How do you lift 20,000 metric tons of steel, heavier than entire naval superstructures, onto a fixed offshore platform while floating in open ocean swells? 15,300 tons, more than the weight of 2 Eiffel Towers, rose from the deck of a transport barge in the Mediterranean in September 2019. At the center of this feat was Sleipnir, Hirama's semi-submersible crane vessel, a platform engineered not just to survive the ocean, but to command it. On that day, Sleipnir's twin cranes, each rated for 10,000 tons, worked in perfect tandem. The load was immense, a single topside module for the Leviathan gas field, destined to become the heart of Israel's energy supply. The operation demanded precise coordination. Every ton suspended from the hooks was tracked by load cells, accurate to within a fraction of a percent. The crane's massive slew bearings transferred forces safely into a hull designed to channel stress through steel and into the sea. To keep the vessel steady, the crew ballasted Sleipnir down to a 32-meter draft, plunging its pontoons deep below the restless surface. At this depth, wave-induced motion drops to a whisper, but the margin for error tightens. The entire lift, from initial hoist to final placement, took less than 20 hours, compressing what would be days of offshore work into a single weather window. Over the course of the campaign, Sleipnir installed 24,500 tons of steel, yet the most critical number was invisible. It was sub-centimeter accuracy in positioning, achieved while the ship floated free in open water. This is not just a story of brute strength. It is a technical puzzle where hydrodynamics, real-time ballast control, structural redundancy, and computational precision must align. The stakes are measured not only in steel and schedule, but in the stability of energy markets and the race to build the infrastructure that powers entire nations. Long before Sleipnir redefined what was possible offshore, 2 vessels set the template for lifting thousands of tons at sea. In 1985, Thialf entered service with a pair of 7,100-ton cranes, at the time the highest capacity ever mounted on a floating platform. Just 2 years later, Saipem 7000 launched with twin 7,000-ton cranes of its own, stretching the boundaries of what could be built and installed in open water. Each vessel was more than a ship. It was a floating construction site, able to hoist entire modules in a single move where smaller ships would have needed weeks of piecemeal assembly. Thialf's rectangular pontoons and deep draft hull allowed it to submerge below the most violent surface waves, making the deck a stable workbench even in rough conditions. Saipem 7000's designers took a different approach, spacing its pontoons further apart and installing a rapid fill ballast system with 40 tanks, giving the crew the ability to shift the vessel's trim and heel in real time as thousands of tons swung overhead. Both ships were retrofitted over the years. Thialf's cranes were upgraded to 8,000 tons each, while Saipem 7000 received a new DP3 dynamic positioning system and 85 megawatts of installed power. These vessels did not just make heavier lifts possible, they changed the economics and pace of offshore construction. With each new project, the demands grew. Larger topsides, taller jackets, tighter weather windows. The result was a race not just for brute strength, but for precision. The evolution from Thialf and Saipem 7000 to today's megalifters is a story of engineering adaptation, where every increase in capacity forced advances in hull design, ballast control, and motion compensation. As the offshore world moved into deeper water and the rise of wind power demanded even tighter tolerances, these ships became the foundation for the next generation of precision lifting at sea. Beneath the deck of a semi-submersible crane ship, the ocean is more than a backdrop. It is an active adversary. Every lift begins with a simple, unforgiving constraint. The vessel must become as motionless as possible, even while floating in open water. The solution starts with the pontoons, giant steel boxes, each the size of an apartment building, submerged over 30 meters below the surface. At this depth, the violence of wind-driven waves fades. Hydrodynamic testing shows a 30% reduction in added mass and wave-induced motion compared to conventional hulls. This is the first line of defense against the unpredictable sea. But stability is not passive. Inside the columns and pontoons, a labyrinth of ballast tanks holds tens of thousands of cubic meters of seawater. During a heavy lift, high-capacity pumps transfer water at rates up to 6,000 cubic meters per hour, redistributing weight in real time. On Sleipnir, 14 rapid-fill tanks can complete a full ballast cycle in under 8 minutes. The goal is relentless: keep the vessels trim and heel within fractions of a degree, often targeting less than 0.15 degrees of heel and a trim error below 5 centimeters. Inclinometers and pressure sensors feed data to a predictive control system, which calculates how each ton of steel swinging from the crane will shift the center of gravity. If the load moves, so does the water, automatically, and with no room for delay. The result is a floating platform so stable that even with 20,000 tons suspended overhead, the deck moves only centimeters. Structural forces flow downward through the hull, but the real battle is against the sea itself. By combining deep draft pontoons, rapid ballast adjustment, and real-time computation, these ships transform chaos into stillness, laying the foundation for the extreme precision demanded by the world's largest offshore lifts. The real secret behind a 20,000-ton lift is not just in the steel you see, it is in the way invisible forces are kept in balance, moment by moment, as the ship and its cranes become a single, controlled machine. Start with the slew bearing, a steel ring over 3 meters wide, forged from high-strength alloy and heat treated for hardness. Every ounce hoisted by Sleipnir's cranes flows through this bearing, which must distribute forces so intense that contact pressures reach 1,800 megapascals at the ring's apex, enough to deform lesser metals in a single lift. Yet these bearings are engineered for over 30,000 cycles, and their surfaces are nitrided to resist fatigue and wear from years of relentless use. Sensors embedded deep in the bearing housing watch for the slightest rise in temperature or vibration, triggering maintenance long before a problem can threaten a lift. But holding the load steady at sea requires more than mechanical strength. It demands active digital control, a level of precision only possible with a DP3 dynamic positioning system. On Sleipnir, a network of GPS antennas, underwater acoustic beacons, motion reference units, wind sensors, and gyro compasses feed a constant stream of data to the ship's central brain. Model predictive algorithms run simulations every second, forecasting how the vessel will respond to shifting wind, current, and the movement of thousands of tons swinging overhead. 6 azimuth thrusters and 2 tunnel thrusters respond instantly, reallocating power and direction to keep the ship within millimeters of its set point. The entire system is built for single fault tolerance. If any one thruster, generator, or sensor fails, the others compensate without hesitation. This is what makes sub-centimeter accuracy possible in open water. The integration of bearing metallurgy, structural load paths, and digital redundancy means that even as the stakes climb, with larger modules, tighter tolerances, and shrinking weather windows, the vessel remains locked in place, transforming a chaotic sea into a platform for precision assembly. The result is not just a floating crane, but an engineered ecosystem, where computation, materials, science, and mechanical design converge to defy the ocean's unpredictability. Every hour a crane ship waits offshore, millions of dollars hang in the balance. The cost of chartering a vessel like Sleipnir now averages $1.9 million per day. But the true pressure comes from the sky and the sea. Over the past 30 years, the number of days with calm enough waves for heavy lifts in the North Sea has dropped sharply. In the 1990s, about 45% of days offered wave heights below 1.5 meters, enough for safe, precise operations. Today, that figure has fallen closer to 30%, according to recent ECMWF analyses. Each lost weather day means escalating costs. A 10-day delay can add $10 to $20 million to a project's budget. The stakes are not just financial. As offshore structures grow heavier and weather windows shrink, the margin for error narrows. Operators must compress weeks of complex work into a handful of suitable hours, relying on advanced forecasting and real-time vessel control to seize every opportunity. The economics of modern energy hinge on the ability to predict and outmaneuver the next storm. Lifting 20,000 tons at sea is no longer the upper limit. The next challenge is already taking shape. 30,000-ton modules, wind turbine foundations the size of city blocks, and tolerances so tight that a misalignment of just 10 millimeters could compromise an entire installation. Offshore wind, in particular, now demands horizontal alignment within 10 millimeters and vertical placement within 5 millimeters. For engineers, this means the margin for error is measured in the thickness of a pencil lead, even as the structures themselves grow heavier and more unwieldy. Meeting these demands will require more than scaling up what already works. Composite metal hybrid crane booms, now under study, promise to cut structural weight by up to 20% while handling the same stress as steel. But the real bottleneck is below the waterline. To balance a 30,000-ton lift, ballast pumps must move over 10,000 cubic meters of seawater every hour, nearly double today's best rates. Each advance in capacity exposes a new vulnerability. A single delay in pump response or a fraction of a degree off in wind alignment could bring a billion-dollar project to a halt. The race for megalifts is a race against both physics and time, pushing every system, materials, hydraulics, and computation to its limit. Right now, every new offshore project pushes engineering to its edge. As global demand drives structures heavier and weather windows shorter, the precision of these giant ships holds energy markets steady. The next record lift isn't just technical, it's economic, political, and environmental. The stakes only get higher from here.